Okay.
Let's do just chapter 8 homework is due today, but I just have a couple more comments to do. I don't know if you have saw the problem where it's in homework or not. Just remind ourselves of a few things first before I make these comments. What's a relation from a set A to a set B?
We need to slow that. Equivalence relation.
What's a relation from A to B?
It's a subset of A cross B.
A subset of A cross B. So it's a set of ordered pairs where the first corner comes from the set A and the second corner comes from the set B. Relation on A.
Subset of itself.
A cross
Of A cross A. So it's just, again, a set of ordered pairs, but both the first and second corner comes from the set A. What's an equivalence relation?
Relate test has find reflexive, symmetric, and transitive properties.
So it should be reflexive, symmetric, and transitive. What does it mean to be reflexive?
It relates to itself.
A relates to itself, so you can write A, R, A, or you can write A is in R for all A in A. Right, so it's equivalence relations, we usually do it on a particular set. So it's on a set A. Symmetric means?
I mean, if A relates to B, then B relates to A.
A, R, B means that B, R, A. So if A relates to B, then B relates to A. This means if the ordered pair A, comma B is in the relation, then the ordered pair B, comma A is also in the relation. And this is an implication, so it can be true vacuously. If you were transitive.
A relates to B and B relates to C, then A relates to C.
Right. And these were the three main properties that the equal sign had that none of the other ordered properties that we have on the real numbers had them. So this was a nice way to kind of essentially boil down what it means to be equal in some sense. Right? So if you look at that at less than or equal to or all these other inequalities that we have, they will fade the whole properties. But the equal sign has it, and so it makes it's a nice element to that equivalence relation.
Professor?
Yeah.
Just one quick question. For the
Yeah? What's your question though?
if I wanted to quantify the symmetric and transitive definition, right?
What do you mean quantify?
Like putting quantifiers on it. So it's
Logical quantifiers? Yeah.
But would I be able to say
It would be a for all quantifiers.
but would would
Yeah, the quantifier will come in the beginning. So this has to work always. So you'd say something like for all A, B, C in A. This is true. They're all universal.
Could I also say like if A relates to B for some A comma B, then B relates to A, and then on all of that say all for all A B? Is that equivalent? Or
No, that wouldn't be.
No, not.
Okay. What I meant to ask about was what is an equivalence class? You can describe it as a set if you want.
It's a subset of the of a or of an equivalence relation.
It's not a subset of an equivalence relation, no. They don't have to be ordered pairs.
It's the set of all A in A such that A is related to B for some B in B.
So we can talk about the equivalence class of A, for example, and that is just a set of all B in our set such that A relates to B. Right? So it's a set of elements of A, it's not ordered pairs. So while I can put an equivalence relation on the integers, and these are just ordered pairs of integers, the equivalence classes are just these sets of integers. And so what are some important things about equivalence classes? Some things that stand out about them. They partition the set. Right, so when you can group every element, if you can put an equivalence relation on a set, it means that you can group all the elements that are related to each other. You put them in sets called equivalence classes, and when you take the union of all these sets, you get the entire set, but they will all have, pairwise, they will have empty intersections. They will not overlap. So you can actually partition the set A using equivalence classes in some sort of equivalence way. So you can use equivalence relation and you can split the integers into odds and evens. You can use them to split them into any other relation you want. Now we also define the integers mod n, or z mod n as some people might call it. How was that defined?
So you have up to n-1 equivalent classes.
So you have the equivalence classes from 0, 1, goes all the way up to n minus 1. And how are these equivalence classes defined? So when I say equivalence class, what am I talking about?
Well, the definition of congruence mod n.
It's by congruence mod n. So here I'm saying it contains all b in the integers such that b is equivalent to 0 mod n. Right? So we're talking about setting up equivalence classes based on divisibility here. And so we look at the integers depending on divisibility by the integer n, and then I can put all the integers into equivalence classes based on the remainder that they have when divided by n. And we know there are a finite number of cases for any given integer by the division algorithm. But this will actually split the integers into, all the integers into a finite number of equivalence classes based on this divisibility. We also define some operations. We define plus and times, where if I take A plus B, it is the same as saying A with the arithmetic addition inside it. And if I take A times B, this is the same as just multiplying inside the equivalence class. Okay. And we actually did a couple tables for each one. So we did for, I think, Z mod 3 and Z mod 4, what the addition table would look like when you add two elements, you look like, and when you multiply two elements, what they would look like. As well as, we noticed some interesting things, at least I think I mentioned it for Z mod 4, is in that we could take two things that are not equivalent to 0 and multiply them and get something that's equivalent to 0, which deviates from how the real numbers behave by a lot. So this set of counting numbers, which sort of is giving a theoretical basis for clock arithmetic, where you just go around to one point and then you start over and keep counting around the clock. It turns out that those numbers do not behave like real numbers, at least not always. It turns out, and I'll mention here, you can attempt it now if you look up the definitions of a field, but you can do after we do go through the second book. turns out that Z mod n is a field. Basically, the short answer, the short of it is, it's a set with two operations like addition and multiplication that behaves just like the real numbers. It will have all the properties that you're familiar with in the real numbers. We call such a set a field. Not all things are fields. So the integers are not a field, because if you divide two integers, you might not get an integer, whereas if you divide two real numbers where the denominator is not zero, you always get a real number. So things like that. So this is a field if and only if n is prime. We can show that. Won't prove that right now because we haven't really covered what we need to say that, but you can read ahead if you'd like. So the next thing I wanted to show was that these operations were well defined. So a lot of times we want to create a definition and it seems plausible and it seems to make sense, but you want to make sure that it actually does make sense. Because you'll have students making this mistake in like remedial math or something, but nonetheless, like they'll think, oh, I just add these two and I add those two, and obviously you should realize that that's not the case. And the reason why is that does not work, meaning you can write the same fraction in a different way and this rule will fail, right? And so that's why you can't define addition that way. The only reasonable way to define this addition is AB plus BC all over BD, right? And so it's not all the time will a rule look very like natural, oh, that's so convenient. Sometimes things might deviate and look weird. So it's kind of weird that when I define this operation by just add on the inside. Seems easy, seems too natural, there might be a problem, so you always want to check when you're defining some sort of operation like this to know that it's well defined. And in the future, sometimes when you're proving things, you'll have to develop definitions in order to prove something, right? So this is sort of how new math gets created. So sometimes we can't really solve things in mathematics because we just don't have the technology, we don't have the land, we don't have the machinery. But if someone just develops the right terms, the right axioms, we can get things to work out. So there's always a concern of when you invent a definition, is it a useful definition? Is it a logical definition? Is it mathematically sound definition? So we'll show plus and times Cn are well defined. Okay. I'll just show for one, the other one is very similar. We'll show for plus similar idea will work with the times. Okay. So the idea is I do not want my definition to depend on the representative that I choose. And that's basically what well-defined means. So basically this means we need to show if A is equivalent to B and C is equivalent to D, then if I do the addition operation with these two representatives, it should be exactly the same as doing the addition operation with the other two representatives. Right? So if I do something with 1 over 2, it should work with 2 over 4, with 16 over 32, with 0.5. It should work with any equivalent representative that I pick. And that shows that it's well defined. And we'll talk a little bit more about functions. I'll give you a more mathematical definition of how you want to think about being well defined in general. But for now, we'll show this. Okay, so go. What do you do?
What equivalence classes A, B, C, and D in Z and D?
Yeah, assume So let's do a direct proof. Assume this and that. Then A plus C is equal to, by our definition, A plus C. How do we know that that's equivalent to saying B plus D?
In the books, like some previous theorem that if two equivalence classes are equal, it implies as if only if the representatives are related to each other.
Well,
And then
sure, that's true. But we can actually use the definition. Like, what does it mean to be this?
oh, and what that works.
A is congruent to C mod, or A is congruent to B mod N.
Yeah, since A is equal to B, this means that A is congruent to B mod N. What does that actually mean? What does that mean we can do here?
Then A minus B is equal to N times some number.
This means A minus B is equal to NK, sure. Also, we know that C is equivalent to D. That means that C minus D is equal to N times some other integer. K, L are integers. Okay, how are we going to use that?
Can you rewrite it?
Then we could solve for A and solve for C.
This means that A would be B plus NK, and C would be D plus NL. This means that A plus C would be equal to, I can replace A with the B plus NK, and the C with D plus NL. And this would be B plus D. Which by our definition is this. What can you tell me about this guy?
Which guy?
This guy, the second equivalence class.
Well, it would also be part of the same equivalence class because, or would it not also be congruent to, well, would it not be congruent to the other two groups? To the other two equivalence classes since
It's zero. Zero.
It's 0. Why is it 0? This is equivalent to 0. And so by our definition, we're adding 0.
all this is equivalent to 0 on n.
Right, because it's a multiple of n. We're in Z mod n. This is equivalent, any multiple of n would be 0 mod n. So the remainder when dividing by this, dividing this by n, the remainder would be 0. So this is actually equivalent to 0 mod n. So this just gives you b plus d plus 0, which is just b plus d. So a plus c will be equivalent to b plus d, even though a and b are just different representatives for the same guy. C plus d are different representatives for the same equivalence guy. So our definition will not depend on which representative we choose. So it's a well-defined thing. You don't have to worry about who in particular from an equivalence class you're working with, because if it works for one guy, it will work for any guy equivalent to that guy. So this is what it means to be well-defined. I think we can end there. So this is a very, very, very important set. It has a lot of nice examples can come from Z mod n. And as I said, Z mod n is a field if and only if n is prime. So this gives you a very special kind of example. You can have a finite set that has only a few elements that behaves. The behavior is very similar to the real numbers, so you can do a lot of useful things with that. It's very interesting that you can do that. Like in terms of these two operations, it behaves like real numbers. Let's move on to chapter 9. Again, familiar territory here. We're going to look at functions, but we're going to want to look at them in, I won't say a completely new way, but just in a slightly more rigorous way. And we're going to want to prove some things about them. We want to be able to do that and just think about them in slightly different ways, because not all functions are going to be very nice like they were back in calculus. So we're going to have to learn to look at functions in a very special way. So here's the definition. A function f from a set A, first thing is not empty, to a set B is, how do you think this function will look?
Pretty similar to our equivalence relations, just with the limitation on
Okay.
the
Is a relation from A to B such that
for any B in B. I don't know exactly how it would work, but essentially there's only one element containing one given B.
For one element, it is one.
no, that's not true. Huh?
For all A and B, there exists exactly one B and B. There's always separate.
Oh, do we get?
For every element in your domain, there is exactly one.
Every A in A appears as a first coordinate. Exactly once. Exactly once. Okay. So there's no real restriction on B. There's no restriction on who they can choose or who they can be assigned to. But everyone must be assigned to someone. So every element here must relate to some element there and be restricted to being related only once. So if I pick one element in A and relate it to B, I can't pick that element and relate it to something else again. Right? This is what creates a function. This is what we call a function. This ABC. Okay. So look at some examples and non-examples. AB 1, 2, 3 equals ABC. Here are some functions. Right, so one thing you need to know from a function, every one in A must appear as the first coordinate. So once you don't have that requirement, you're not a function. They must also appear once. So a function looks similar to this, and I can just choose things from this guy. So I can go like B, A, C. That would create a function. Or choose A. There's no requirement on the second coordinate. I can reuse second coordinates if I want. A function only gives a requirement on the first coordinate. I can use 1A, 2A, 3A. To do that. These are all examples of functions. There are some things that are not functions. So you'll notice that this is not a function. Why? Because 1 appears as the first coordinate in 2 ordered pairs. Also, 3 does not appear anywhere. So the element in 3 never appears as the first coordinate, so that's not a function. Similarly here, the element 3 never appears as the first coordinate, so that's not a function. Elements 2 and 3 do not appear as first coordinates, that's not a function. Here, everyone, 1, 2, and 3 appear as first coordinates, but 2 appears as the first coordinate twice. 2 appears as the first coordinate twice, therefore it's not a function. So functions are just very special kinds of relations. Some more definitions. A is called the domain of the function. B is called the codomain of the function. And if I look at things like is a function from A to B, then we may write this notation, F colon A to B. So if it's not understood, you can write it out that way to say who's your domain, who's your range. I'm going from this guy to that guy. We also have the other notation to say that if C is a subset of A, maybe I should just define for coordinates first. So looking at notations here. Second of all, if A comma B is a member of the relation F, that is a function, then we may write F of A equals B to denote that relationship. We also have the idea that if C is a subset of A, then F of C is so in a function, we can plug in particular elements. We can also plug in subsets. And the notation will follow frankly, in this way. F of C will be the set of all B in B such that F of of C equals B for some C in C. This is called the image of C. We can also talk about f of A. This is called the image of A. This is also called the range of the function. So this is going to be the set of all B in B such that f of A equals B for some A in A. Right? So if we are looking at the set of all people who are assigned, who happen to show up as second coordinates, granted they don't have to show up, but the guys that do show up, we call them the range, we say that they're in the range of the function, or they're in the image of the domain. These are the language that we use. So, example. Introduce another notation. I can say this is ran f for the range of f. So, example. The range of f1 was well, order doesn't matter in the set, so it's that, which happens to be the entire set B. What was the range of f2? It's literally just the set A. Notice that it's a subset of B. By the way, the range is always a subset. Because you are choosing elements of B, just the ones that were assigned in your function. And also the range of f3 would just be the pair AB, the set of two elements. Notation is going to be important because it's going to help us prove a lot of things. Okay, introduce stat notation. F is the name of the function. Another language thing here, just in case. If f of A equals B, we may say any of the following. F maps A to B. We could say F maps A into B. We can say B is the image of A under F. There's some language there just in case you see it in the book. Two functions, f from A to B, g from A to B, said to be equal. Generally, if f of A equals g of A, right? So for each corresponding input, their outputs will be the same. For all A, and here f equals g in this case. Sometimes use variables to denote domain and range elements. So we can call f from A to B by f of x, where this guy variable that denotes some domain element. We can also say y equals f of x. This would be the variable that denotes corresponding image of A. The domain elements can be called inputs, while the range elements are often called outputs. So here I can say x represents some generic input, something that I can plug into the function. Notice that it is a domain element, it must come from your first set. Y can just be a variable that represents the corresponding outputs of the input x. So language is just as important sometimes as math, so I want to make sure we're all on the same page with that. Now let's look at ways to express and visualize functions. One is as a set of ordered pairs. As previously shown. So when we wrote f1 was equal to 1b 2a. Alright, so you can just write a list of ordered pairs. This denotes what we call a single variable function, which we're not going to talk too much about multivariable functions here. But in multivariable functions, the elements in your pair can also themselves be ordered pairs, or maybe even larger things. But we're not going to get there for now, we're just keeping it basic. So a set of ordered pairs is one way to represent a function. Sometimes it's useful, especially if you're dealing with things that are finite domains and finite codomains. You can just list everyone, you can do that, and just, in some cases you might want to brute force something. That would be a way to list things. But there are other ways. They're what we call mapping diagrams. These guys are important in the way that Venn diagrams are important. They can help us to come up with theoretical ideas of how we might want to approach a problem. And we'll probably use this later on when we're doing some proofs about functions. So they're mapping diagrams. So that's when you literally draw a picture of the domain and range. So I can say A, and I can draw a circle that contains A, that represents a circle that represents a codomain B. And I can have the three elements here, 1, 2, 3. And I can write B here, A, B, C. And if I looked at the function F1 told me that 1 connects to B, 2 connects to A, and 3 connects to C. If we look at F2, it's 1, 2, 3, A, B, C. I think F2 was the constant function. Everyone went to A. From what I remember. So you can have that. What tells you that it's a function is the fact that every element in A has a line leaving that element. It has exactly one line leaving that element. Right? So that what makes a mapping diagram. You can map other kinds of relations, so we can map things that are not functions. So if we looked at, for example, G1, here was A, here was B. And let's also look at the last one I did, G4. These are not functions. So if you're visualizing a function this way, you can easily tell if something is a function or not. So this is 1, 2, 3. This element is 1, 2, 3. This element's A, B, C. This element's A, B, C. In G1, did 1 relate to anything?
To A,
1 related to A.
2 times.
What do you mean 2 times?
You said was 1 comma A, comma 1 comma A, comma 2 comma B.
Oh, so let's that be 1 comma B, because 1 comma A is the same thing. So let's say 1 goes to A and B, 1 comma A and 1 comma B, and 2 comma B. 3 did not leave anywhere. Notice that this is not a function because we have 2 lines leading 1, and we have no lines leading 3. So this guy breaks the rule of what a function is in 2 ways. 1, you can only have a guy related to one other element in the codomain, as well as every guy must be related to someone. So the fact that 3 is not related to anyone makes it not a function. G4, what do we have? 1 comma A,
2 comma
the 2 comma A,
2 comma B,
the 2 comma B,
3 comma A.
3 comma A. So again, here now everyone here gets assigned to someone, but 2 got assigned twice. Here we have 2 lines leaving 2. So that's a problem. Okay, so that's how pictorially you can talk about a function. And if you want to try to create a function with a certain property, a lot of the times what you can do is you can just draw a picture and just try to see, can I connect things in such a way that obeys some other rule that I want? And that can give you an idea as to whether or not some theorem you want to prove is correct, or whether or not you might want to, you're able to create such a function. These mapping diagrams can come in handy. It's another way to represent a function. Of course, there are formulas the guys are used to, which we'll also use these. So, for example, I can talk about f going from r to r by f of x equals x cubed. So this is when you can describe what your function wants to do in terms of arithmetic operations or some other mathematical operations, and you can just write down a formula for what this function will do. And this function will actually connect every element x to exactly one element in the real numbers called x cubed. So we have 1, 2, 3, da, da, da. So this will go to 1, 2 will go to 8, 3 will go to 27. We can have pi here, that will go to pi cubed. Where that's not the main range. And of course there are many others. So you can actually describe it as a function, and we're very familiar with that. That's a lot of calculus was based on us looking at functions in that way. So I'm not really going to say anything more on that for now. I know so far a lot of this is familiar. I just want to make sure we're all on the same page. Of course, they can do graphs. So now we represent a function. So again, if I look at f from R to R, one way we can visualize this is to think of this here, where the set of all R's come from. And we can call this guy, of course, we call this the x-axis for the generic. If we're setting y equals f of x, call that the x-axis, and we call this the y-axis. So elements from the codomain are here, elements from the domain are here, and we can actually pick elements. So I can say here f of x equals x cubed. So it means that I plug in 1 goes to 1 cubed. That is the coordinate 1, 1, and 2 goes to 8. So we can plot that coordinate. If you plot all the coordinates, you'll get the graph that looks like that. So that's a picture that gives us a graph. We can also plot things like F1, where we have 1, B, 2, A, 3, C. So something like that. I can use this to represent the guys that come from A, the guys that come from B, and I would have 1, 2, 3, and let's say here I put A, B, C. And I can go to 1 goes to B, 2 goes to A, 3 goes to C, and that would be a graph of that function. So it's just a pictorial representation. Let's define the inverse image. Then we'll prove a couple things we can just not be bold. Suppose f goes from A to B, and let D be a subset of B. We call this set, and that's the notation. The set of all A and A is such that is an element of D, the inverse image. We'll define inverse functions in general a little bit later, but that would be the inverse image. So, example, our F1 was 1 goes to B, 2 goes to A, 3 goes to C. So if I let, for example, D be the set AB, then if I take F inverse of D, this is the set
Is this still using the same A that
It
we?
will just be 1, 2. Yeah, I'm using the same F1 from way back. Alright, so these were the elements in A that the outputs were A and B. So that defined the inverse image. Inverse functions come a little later, so we'll define those. Let's actually do a proof of some things here.
So the inverse image is a subset of A, right?
It's a what?
The inverse image of E is a subset of A.
Yes. It might be all of A, but it might not be. We can also talk about F2 was the constant function I used, so this is that one to the A, this one to A, this one to A. So if my D was a set B and C, what is F inverse of D? The empty set. Because under this function, no one mapped to B or C. I could also, I could say if D were just a set containing A and B. Then the inverse image of D is actually all of A. Right, these are elements in A that map to some element in D. I could also this extends to one element sets, which we call singletons. So I can talk about the inverse image of a particular element, which sometimes we informally might write that. And that's just the set of all A in A such that f of A equals B. So I can talk about, for example, F1 inverse of the element C is which element? And I can talk about F2 inverse of the element A, talk about F2 inverse of the element C. What's this guy?
Set 3?
Just a set containing 3. That was the only guy that mapped to C. What was F2 inverse of A?
A.
Big A, right? Everyone knew to A. What's this guy?
Empty set.
It's an empty set. Right? No one mapped to C in F2. Okay. We'll do an example of a proof. Start to put some ideas together, then I'll introduce some more definitions. I mean, a lot of the functions, I'm going to be introducing definitions. We're going to use functions a lot in chapter 10. So a lot of this would be us rehashing things that you already know. I understand it might be boring, but I want to make sure everyone's on the same page and we fully understand what I mean. But here's probably something you never did in Calc 1 or Calc 2. So here let f be from a function from A to B, and suppose C is a subset of A, D is a subset of A, E is a subset of B, and F is a subset of B. Show two things. show that the image of a union is the union of the images. You show that the inverse image of a union is the union of the inverse images. Facts like these you'll use a lot, like in your homework. You will use things like these as lemmas all the time. Okay, go.
For them to be equal, that subsets of each other?
Right, remember these are sets, so we have to remember what does it mean for sets to be equal. We need to show that this set is a subset of that, and that set is a subset of that, because these are sets, so we need to show two things. 1 and 2. 1. For the first inclusion, how would I show this is a subset of that? What does that even mean to show that? Right, if I assume there's some element in here, that element must be in here. So let's actually try that. Let's actually try direct proof. Assume I have some y that is in f of c. How would I know that that element is in f of c union f of d? Then
There exists some element in C.
Then there exists
Some element X in C union D such that f of X is equal to Y.
okay. So what can that say?
Cases.
What are the cases?
So suppose X is in C and D means X is in C or X is in D.
This means x is in C or x is in D. So
Could it be both?
Could be both. if they are overlapping. With all loss of generality, though, let's just assume it's in C. Then
F of X or F of C would also equal Y? Or then there exists an X within F of C such that
So then this means your y would be an element of f of c, right? Which would then imply, by the same thing, same idea, that x is an element of the inverse of c. But that would mean, if you're in one set, you're in that set union with any other set. So that proves the first inclusion. So the idea here is I have a set here A, I have a set here B, I have one guy here, that's C, one guy here, that's D. They may overlap, but this might be empty. I have another set in here that we call E, I have another set in here that we call F. But the idea is, I'm looking at instead, I'm not focusing on E and F in this statement. I'm focusing on the guys that map from C, where do they go? They go into a set that we call F of C. And the guys that map from D, where do they go? They go into a set that we call F of D. So my claim is, the union of these guys will map to the union of those guys, right? By taking a union here, I'm not going to exit these sets. I can't take a union and plug a guy here and get someone that's outside this union.
Why do you show that x belongs to the inverse to that, as opposed to just that?
Oh, because I was looking at it differently. I was looking at this.
Oh, okay. Oh, next one.
That proves the first equilibrium. What about the second one? Assume the other way. Y is an element of F of C union F of D. Then we know that Y is either in this guy or Y is in that. Without loss of generality, assume Y is in this guy. Then this means there exists an X in C such that f of X equals what? But X in C implies that X must be in C union with anything. Which means that Y must be an element of union. That proves part A. Let's look at part B.
Professor?
Yes.
That last proof, the previous one, right? This one, is there something wrong with the letters? Like the X's and F of C was really Y in F of C?
I think it was supposed to be F inverse. Since if X is an element of C and Y is an element of F of C,
You first chose to say that Y is an element of F of C union D, right? So then we have to show that Y is an element of F of C. Or you meant to say Y, right?
At what point?
The last and the end.
Yeah.
Here, yes.
The end of the previous.
well,
And so the line on top means. So I
I
said,
think it's a
without assume X is in C, then that means technically
Professor, if
then
you,
Y is in this. Yeah. So this was.
could you say that X is an element of F inverse C?
X is an element of F inverse of C, yes, but part A didn't care about the inverses, so that's why I didn't
I
use it.
thought it was like F is an element of X is an element of F inverse C, so X is an element of the union of the inverses, so Y is an element of.
Yeah, but I was looking at part B when I wrote the inverses thing. Part A didn't have inverses in it at all, so I wouldn't say anything about the inverses. Even though it would be correct to say that, it wasn't what I cared about at the time. B cares about inverses. So here we need to show that the inverse of a union is a subset of the union of the inverses. And the union of inverse images is a subset of the inverse of the union. So part B1, part B, part 2, 1, if we assume X is in that. And notice that how I choose my variables wisely so I won't mix up. We're used to thinking of, and I don't want you guys to get used to letters per se, but we're used to thinking of Y as an output and X as an input. It's important that you realize that this is a subset of A, right? So you want to use suggestive things that at least remind you that, okay, I'm looking at things that are in A now. Okay, so assume X is in this. What does that mean?
F of x is equal to y.
So we know that f of x equals y
Some y.
for some y that's in this union here. But that means that y is in E or y is in F without loss of generality. Assume y is actually an element of E, then this would give that x must be in the pre-image of E by our definition. So this would mean that X is an element of that set union any other subset of A. For 2, if we assume X is an element of F inverse of E union F inverse of F, then X is either an element of this guy or perhaps not exclusively, but an element of that guy without loss of generality. Suppose it's in the first one. Assuming it's in the second one, would be a very similar thing. Then there exists y in E such that f of x equals y. But y in E implies that under y is in E union F. This means that where X is also in the inverse of the union. Right, so we have to remember a lot about sets as well as now we're applying what we know about functions to sets. And you really need to rely on your theoretical knowledge, not just an idea of a picture of what you think of being an inverse is, or a mapping diagram, just think of it as the guy that connects backwards. But what does this as a set mean? That was just a little proof there, change of pace. Let's get back to some definitions. Set of all functions And this is a very useful idea to think about. Not only is it useful in its own right, but it is also useful in terms of, it has a lot of theoretical advantages to consider this set. And when we get to chapter 10, we'll actually use this to our advantage as well. So the notation here is BA. B raised to the power 8. This is the set of all functions f such that f from A to B is a function. Right? So this is a set of functions. Look at all possible functions that can go from A to B. There is possibly an infinite amount of them, right? So I can think of the set of functions from the real numbers. So the real numbers, there's an infinite number of those guys. So you can have a finite case as well as the infinite case here. Let's look at some of them. Let's do an example to give you a concrete idea. Example, let A be the set 1, 2, 3. B be the set AB. Then tell me some functions that can go from A to B. And you could even do this in the table form if it's easier for you, where you can do that kind of like manipulation that we did when we were creating truth tables. Come up with a pattern to make sure you're not missing anyone. You can probably also do that here. Just make sure you list the functions vertically and kind of line things up so you can see if you're missing anything. We'll come up with an argument. We won't do it rigorously, but we'll come up with a little argument to say how many there should be. Let's look here. So, yeah, what's one possibility? I can do everyone A. What's another possibility?
Everyone B.
I can do everyone B. Let's do this kind of A and change that guy. Or I can do AB and change the 2.
Or BAA.
A, B, B.
Or BAA.
B,
BAA.
A,
BAB. BAB.
BB. What?
BAB.
B, A, B.
B, B, A, and B, B, B.
Are there any other possibilities?
Nope.
Right. So notice here, you can notice the little principle that's going on. And this will look like a truth table, kind of. You'll see the same sort of principle happening, but that's because there are only two options. You can do these as either true or false. So you alternate here, alternate every 2 here, alternate every 4 here. And that gives you a strategy for figuring them out. You can realize that for your A, you'll always have 2 options. One will either go to A or B. The same thing will happen. You just need to do all possible rearrangements of this. And in this case, there were 8. Now, what do you notice about that guy?
2, B, A, 2,
It was 2 to the 3.
Cardinality.
Wait, is it
Cardinality.
Cardinality, right. So why the notation? You might think the notation of taking a set and raising to another set is weird, but this is why. It's algebraically, it's a natural way to write it. Here's why. Because the number of things in here is actually just the number of things here raised to the number of things there. If A and B are finite numbers, of course. We have infinite numbers, chapter 10, we'll need chapter 10 to deal with all the cases there. Okay. So the number of functions, the number of possible relations that you can make from a set A to a set B, such that the relation is a function, we call that set B raised to the A. And this, in the case that both our sets are finite, this is the number of functions that there will be. So you can always know if you're missing functions or not. And sometimes you might not have to list them brute force, but knowing how many there are can tell you a lot of things, and that can help you out in a lot of cases. So, here's something that's common. If you have something like these from 0, 1, 2, up to let me do a specific case first. So a binary situation is often comes up, like 0 and 1 for on and off. Then B raised to the A is denoted, this is the notation that we use. We literally just say 2 raised to the A. Right? So when you see 2 raised to a set, you're kind of thinking of this kind of relationship. So in the future, like in chapter 10, you'll see things like 2 raised to the real numbers. Like, what does that mean? It means this, right? All the possible functions that you can take where the domain is the real numbers and the codomain is just a set of 2 elements, you can describe all such functions by this notation. And of course, if you can put 3 elements, you put 3 to the A and 4 to the A. So if you see a number raised to a set, how do you interpret that? It doesn't have an arithmetic interpretation like you would normally be used to. It has a set theoretic interpretation. So this is so you can think of this far more generically. All sets from A to a set containing 2 elements. And so we can say if n is a natural number, n to the A equals all functions from A to a set with n elements. We have a lot to go over with functions, but again, a lot of it's familiar. We're going to talk about one-to-one and on-to and bijective functions again, but being very careful how we're defining things so that when we need to prove something, we can. So you'll see this guy show up later on in chapter 10, probably in your homework as well. more familiar ideas, but we're going to make them more precise. One-to-one. And onto functions. A function f from a to b is called injective or one-to-one, or sometimes we can just write 1-1. If there are two equivalent ways to think of this, I'd rather you think of it as an implication. If f of x equals f of y implies that x equals y. Or equivalently. If the inputs are not the same, then that means the outputs will not be the same. So before in our functions, this actually puts a requirement also on the second element, the output element. Right? So someone can be chosen as an output by only one guy in your domain. Right? You can't have several guys going to the same output. So something like a constant function, for example, would not be one-to-one if you have several things going to the same thing. So one-to-one just means each person maps to one other person. You'll never have, so this guy will map to one guy. This guy cannot go to a guy that's been chosen before. Everyone has to go to someone separate. So that's what a one-to-one function would look like. Something that's not one-to-one would be like, he goes here, but you have this guy also going there. Or you can have a constant function where everyone goes to the same guy. These are not one-to-one. Just an example of one-to-one. Okay? So each guy, once someone is the output of someone, no one else can have that output, right? Meaning if the outputs are the same, then the inputs must be the same. Or you can say different inputs go to different outputs. But ultimately, if you need to prove that something is one-to-one, you need to prove either one of these implications. That's probably how you thought of it before now, but here I want you to think of it in terms of an implication. We can also talk about surjective. F from A to B is called surjective or onto. If, and this one is slightly more cumbersome to write down. If for all B in B, there exists, so it's a quantified statement, x in A, such that f of x equals B. This is an idea that i.e. the range of f is the set B. Every element in B is assigned to at least one element in A. But I'd rather you memorize that definition. Yeah.
Say if I wanted to quantify the one-to-one definition, the injective one, would it be okay to say for all x in A, there exists a unique image B under function f? Would that be okay? And would that be acceptable?
there exists a unique image.
For every x a.
You could say that, yeah. Just make sure you realize that when you say unique image means that any other image could not be mapped from X. But yeah, this would be a universal quantifier. It will have to happen all the time. This means there is some sort of an existential quantifier, and it doesn't have to be unique. So every element in B is assigned to at least one element in A. So you can look at ideas here. So let's say A has 2 elements, then that is a onto function. You can have 3. So we could be, so this is onto and 1-to-1, which is something a comment I should make. These guys are exclusive of each other. You don't have to be one or the other. You can be neither, you can be both, you can be one but not the other. They don't have to happen at the same time or at all.
But
Yeah.
is it possible to be a one-to-one function and not be onto?
Oh yeah, that's easy.
Oh, if
And
there's
this
B
is
with
sort of,
no-
and this is sort of getting into a little bit of chapter 10. What if this guy had more elements than that? Then that's 1-to-1, but it's not onto, because there's someone here that's not assigned. That's an idea that we'll expound on. What's the difference between these two? And we realize why on 1-to-1 and onto are things that we care about, and why having both is a really nice thing. So these are one onto. I can give you non-examples, not onto. Two guys in here, one guy there. If f from A, B is onto, we say f maps A onto B. So you can map it right on top of the guy. That's the language that we use. So the outputs will cover everything. So once you arrange the entire codomain, we call the function onto. If each input gets a unique output, we call the function 1-to-1. Right? Every guy will connect with one other guy, that's 1-to-1. This you might call something it's a function still because it obeys the rule of a function, but you would call it a many-to-one function. Right? So a many-to-one relation is a function, it's just not a 1-to-1 function, it's a 1-to-1 relation. If you have a 1-to-many relation, that's not a function, so that would mean you have the same guy mapping to several other guys. Okay, so that's what 1-to-1 and onto means. So 1-to-1, unique inputs go to unique outputs. Onto means everyone in your codomain, there is someone in your domain that gives that guy's an output. So if you're ever asked to prove that something's 1-to-1 or onto, you need to use these definitions. Pretty much out of time, but let's just do one more definition. F from A to B is called bijective, a bijection, or a 1-to-1 correspondence. If F is both 1-to-1 and onto at the same time. Remember, it could be both, it could be neither, it could be one but not the other in either case. But when it's both, that's nice, we call it a bijection. We'll talk about some consequences of bijection and how they tie to inverse functions, and how they can relate the two sets together next time. So we'll stop there for now. Be sure to leave homework 8, and I'll see you guys tomorrow.